I'm Elena Green from Livermore National Laboratory, and today I'm going to be telling you about a project I've been working on called Pseudopod, or a method to emulate SubUIDs using seccomp and ptrace and that kind of wizardry. So if you were here earlier, you probably should be familiar with SubUIDs. This is the sort of intermediate privilege sort of user namespace mapping thing that Reed was talking about earlier. All right, so a bit of background. The Charlie Cloud developers have proposed a three-tiered taxonomy of container runtimes, with tier 1 being or type 1 being the most privileged, and type 3 being the least privileged. The main way that these things differ is that type 1 is essentially, if you are root in your container, then you are actually root. So this is typically how things like Docker work, and that's problematic for reasons I'm sure you can guess on HPC and shared tenancy systems. So type 2 is kind of an intermediate middle ground where instead of having root, you're still yourself inside the container. It's just you use user namespaces, privileged user namespaces in this case, to look like you're root. Now, the privilege in the privileged user namespaces comes from the SubUID. And in this talk, I'm going to be using the term SubUID and SubGID more or less interchangeably. I'm probably only going to be talking about SubUIDs, but everything with SubUIDs also applies to SubGIDs. So the problem with privileged user namespaces is that while they do allow you to call setUID within your container and have it appear as if the setUID works, the problem is that when you do that setUID, it actually changes your ID outside of the container as well, and that can have a number of issues. So, for example, because it's a one-to-one mapping, if I set UID to a different user, then I need to have that ID range accounted for somehow. Otherwise, a user could use that mechanism to impersonate any other user on the system, and then we run into the problem of having it be basically a real root situation again. The other problem is that this also allows you to potentially access files that you shouldn't be allowed to access, and you also have to really trust that setUID helper that you need to set up the privileged namespace, because if it gets it wrong, then you get all these kinds of container escapes and potential CVE situations. So type 3 is really, in my opinion, the ideal sort of approach to this. Type 3 is fully unprivileged, as in like anything that you do inside your container is something that you can do yourself without using the container runtime that you're using. Like if you just logged into the system, only had access to the login node and the ability to compile code, you can do it without having to ask the sysadmins to do anything else. So there's really no probability or no chance for container escape with a type 3 because, well, once you escape the container, you're still just yourself and you can't do anything new. So at the moment, type 2 runtimes are the most common. These are things like Podman, and I believe Singularity and Charlie Cloud still fall into this for the most part. So Podman is kind of weird because it does work in type 1 mode if you are root, but it works in type 2 mode if you're not root and you don't have any extra permissions. So some of the limitations of the type 3 runtime, though, are because you only can map one UID into the container. Things like setUID and chown don't really work out of the box. And that's where Charlie Cloud has sort of, I guess, led the industry on this, using the seccomp-based fake root implementation. So, and a little bit background on seccomp. So I mentioned that a type 1 container is basically root. So you might be wondering, like, if you're basically root, then how can things like Docker allow you to, actually run on a shared tenancy system? There's a number of services that let you run Docker containers, and that is where seccomp comes in. You can think of seccomp as kind of like a firewall that sits between your application and the kernel. Once the firewall is applied, the application has absolutely no control over whether or not that firewall is used or not. You can add additional rules to it to restrict it even further, but you can't remove any rules. So for the most part, when you're using a Docker container or Podman or anything like that, you have a set of seccomp rules that have been applied to the container processes. And this usually just prevents you from running specific system calls like, mknod, which would then allow you to create a device and then do arbitrary things to that device. It can do pretty fine-grained filtering, like say that you can run mknod, but only with these specific parameters. But essentially the way that it's used mostly in industry these days is to prevent you from doing things that you otherwise shouldn't be able to do. Charlie Cloud does this a little bit differently, because Charlie Cloud uses this mechanism to provide an inconsistent root emulation. And the way that works, and Reed went over this a little bit earlier, is one of the mechanisms or one of the behaviors that you can use seccomp for is to return an error number, essentially. And in the Linux kernel space, you call a system call. The error number is the result of that system call. So if you run getUID, then you would expect to get the UID back. But actually, what you're getting back is an error number. Like it's really just kind of like call semantics at this point. But the UID is the error number that's returned from the system call. So when you have if you set up a seccomp rule that says when I get this getUID system call, return 0, then when you call getUID, it looks like you've gotten a 0. Hopefully that makes sense. I'll just I have a little graphic here to demonstrate how this works. So when you call getUID in user space, instead of going to the kernel, it gets intercepted by your seccomp filter, and then that simply checks the rules. It says, well, I've seen this, I need to return 0. And then it just sends 0 back to the user space. So from the user application perspective, the system call worked. You got a 0 back. So there are other things that we can do with seccomp. And Reed also mentioned this earlier, but one of the things you can do with seccomp is you can invoke a ptracer on your process. And this works the same way as like a breakpoint, as if you had a debugger attached to it. I'll just have a little graphical demonstration here. So this is an example of a system call that is not intercepted. It is a system call that we don't really care about. We just want to get the process ID. And we don't need to care about this because all we care about is UIDs and GIDs. So in this case, we have our seccomp filter that is not filtering on getPID, so that goes straight to the kernel. It executes in the kernel space as usual, and then returns 3721 back to the user. So where this seccomp ptrace thing differs, though, is we have a seccomp filter that has a rule that says when we see the setUID or getUID system call, then we intercept and then redirect that, invoke the ptracer. Then, well, I'll go back a couple slides and then talk about sudo, I think.
So, sudo and libsudo are the project that I'm talking about in tiling and technical content. That is a PRC framework that I've written that does the ptrace and seccomp side of things. The idea is that you have a seccomp filter that looks for specific system called the getUID and setUID, and the libsudo side of it is what captures the events from the seccomp filter, and then just determines how to handle them. At the moment, it does a more or less one-to-one implementation of what the system calls will do in the kernel if you were actually privileged. So the kernel has like a bunch of complicated behaviors around setUID and getUID, or I'm not saying the scope of this, but there's some fine-grained behaviors because we essentially have to create calculations at any given time with this mechanism. But libsudo more or less implements those in user space using ptrace and physics. And then getting on to this, when we run setUID, libsudo or Pseudopod, it captures the ptrace event, sees that you were trying to run a setUID call, and then determines that because you were trying to run a setUID call, we need to update or kind of simply refer that PID to the new ID that you were attempting to set. So in order to do this, we have to have a state table instead of pseudo that just correlates the process ID with the user ID. And Linux works a little strange in terms of process IDs because normally you think of a process ID as being a specific process, but in fact in Linux threads also have process IDs. And there isn't really a differentiation that's between threads and processes per se. So the PID is also unique for thread. So we update our state table with the requested UID, and in the future, if we get a get UID call that attempts to get the UID, we have the same thing where we figure out that we're doing a get UID, seccomp stops it and goes to the tracer, and then seccomp picks up the feature's event signal, sees that we're running a get UID system call, determines that we need to fetch whatever user ID is stored for that process, grab that from the state table, sets it as the return value from the system call, and then continue with the code. Here's just the one implementation details for how to do that. So one of the challenges to doing this is that when we started with the process, that information, the build and GN information is inherited from the parent of that process. So we need to keep track of which processes are the parents of the other processes in order to maintain the system data. We could be setting the data to 1,000 and then server data to process to prevent it from coming to a shell. But we would also expect that the data of the child process to be 1,000. So there's, we have to keep track of when you create a process, and that's mostly by catching the goal for creating roles and roles, which create building processes. So ordinarily, when you think about using ptrace and any kind of thing like that to emulate system calls, we think that this is going to be really slow, because traditionally it is really slow. But when we use seccomp to target the exact system calls figured,
Sorry about that. Yeah, as I was saying, normally when you're using ptrace to emulate system calls, you expect that to be pretty slow because the typical traditional view of ptrace emulation is that you need to do recursive attaches to all of the child processes. You need to catch every single system call, and then in ptrace itself, check the system call and make sure that that system call is something that you care about. And if it's not something you care about, then continue. So when we use seccomp, though, that allows us to target a very specific set of system calls that we do care about. In this case, getUID and setUID. And there's a couple others as well. So to test what the overhead of actually doing this with seccomp was, I wrote what I call a pathological example. And that's essentially a fork bomb that just calls getUID, setUID, and then getUID again. And so the program calls getUID, setUID, getUID, exit, and that's basically it. And then it's essentially just like an 8-level fork bomb with a fan out of 8. It slows down the system quite a bit when you run it. It turns through a lot of process IDs. So this runs about 250,000 simultaneous processes that are all just doing only the system calls that we care about. So it is the absolute worst case. And as my benchmark numbers here show, our overhead is roughly 50%, which is, not great in terms of overhead. But if you consider that the entire workload is being intercepted and emulated in user space by a single thread, it's actually not that bad. So for like a more typical use case where you're doing like a container build or building a code or something like that, the overhead is going to be essentially negligible because most of those things don't even call getUID or setUID. So just to have a bit of a shameless plug for my project here, Pseudopod is something that I wrote to address a problem at Lawrence Livermore, which is running Podman. So we have a very complicated mechanism to set up SubUIDs and sub-GIDs and all that. Pseudopod is my attempt at stopping the further proliferation of SubUIDs and sub-UIDs in our HPC center. And I am currently working with the Charlie Cloud team to hopefully integrate this into Charlie Cloud as a sort of a fake root plus plus kind of thing to provide at least some semi-consistent fake root capability. So future steps are, at the moment, we're using seccomp and ptrace. Linux kernel 5.0 gives the ability to use something called a unotify or a seccomp unotify, which is a notification file descriptor that you can attach a thread to, and the kernel will send the events to the notification listener instead of using ptrace for everything. So that would allow us to completely remove ptrace from the equation. That has a couple It has a couple issues at the moment. First of all, that it requires Linux kernel 5, and unfortunately at Lawrence Livermore, we're not running a 5.0 kernel yet. And also, there's some lingering issues relating to the state tracking of when you create the when you create the process with the fork and clone system call. It's not as easy to catch those. So, yeah, I guess that's about it. If there's any questions, I think we have a couple minutes left. Yeah.
So I think you said earlier that when you have a semi-privileged container, that if you have the SubUID set inside the container, it gets reflected outside the container too, and then there's some problem there. So I was wondering what your perspective on that is, if like we're trying to sandbox containers, right? Especially if we're wanting to use agents.
Mm-hmm.
So does that apply in this sandboxing case, and like what are your thoughts on that?
So is your question specifically like if we're trying to fully contain whatever's inside the container?
Yeah, so like I guess if I think about sandboxing, I want my agent to stay in the container world. I don't want it to escape, because then that would be really scary. So when you brought up the SubUIDs getting reflected outside a container too, then I think that what that would mean is that then if an agent adopts your UID, then you can pretend outside the container go do stuff, right?
Mm-hmm.
Make run processes and syscalls. So I was just curious, like, what is your take on that, or like your perspective? Any insight, like, you know, yeah.
Yeah. Okay, so I think the question is how SubUIDs affect like the ability to keep something inside of a container contained. And so SubUIDs, I've mentioned that I don't really like SubUIDs because they do change your user ID outside of the container. And so normally you need to have a privileged helper to set that up. And there's some configuration files like etc SubUID and etc SubGID that specify which SubUIDs you're allowed to map. But those files are actually only interpreted by the, more or less standard SubUID setup helper, which is new UID map and new GID map. So you're really trusting that new UID map and new GID map are doing the right thing there. So I guess the problem with SubUIDs again is that like when you set the UID outside or inside the container, it does change it outside the container to one of those SubUIDs. So from inside the container, that's not really visible. And if you have the correct like accounting and security stuff set up outside the container, then that's less of a problem. There's we have some things that are evaluated based on your UID. And we've had to add like special rules to say like if your UID is not inside like the normal range, then we assume that you're a SubUID and treat you with like extra caution. But running a process with a SubUID is like if you look at top outside the container, it will be that random SubUID or like the giant number for the SubUID instead of like a normal 0 to 65K SubUID or normal user ID. So yeah, there's always just extra problems when you allow a user to actually change their UID like that. Like one of them being like accountability, as you mentioned. So if your agent is able to evade accountability by setting UID to some other UID that it's able to, if you don't have like a way to track that back to the user that originally invoked it, then you won't be able to know like who was using that SubUID at that time. I hope that answers your question.
Oh, that's great. I had another question.
Yeah.
Can we go to your picture with ptrace and the seccomp stuff? Yes.
Which one?
Actually, this one might be fun.
I think it's lunchtime, so folks want to go ahead to lunch. I can talk more. Sorry.
Yeah, and I'm available if you have any questions.